In this last section, we are going to talk about empirical formulas, and we will also talk about molecular formulas and discuss the difference for each. We will also work out a few problems. The empirical formula tells us which elements are present in the simplest whole number ratio, but it is not necessarily the actual number of atoms found in the compound. On the other hand, the molecular formula, that one provides the actual number of each atom in a compound. Sometimes, though, they're both the same. Like in the case of vitamin B12 and others, it will have the same formula. Okay, so this problem is split up into two parts. In the first part, we're going to find the empirical formula. In the second one, we'll find the molecular formula. In order to find the molecular formula, you must have the empirical formula. So you might have these type of problems that are split up into two parts, or you might just encounter problems that only ask you for the empirical formula. So I wrote here a few steps that you can follow in order to find the empirical formula. So the first one says that you need to convert grams to moles. And right here, we're dealing with percentages. But basically, here, we're going to take this into consideration. 1% is basically the same thing, in this case, as 1 gram. So we are going to write that here. 37.02 grams of carbon. And we're going to convert that to moles using the molar mass of carbon. And it gives us 3.08 moles. And we're going to keep on doing that for every single element that is listed there. I'm sorry. Not like that. Okay, we're going to divide it by 14.01 grams per mole. And the last one, okay? So this is the first step, like I mentioned. After you obtain all your moles for each element, you're going to have to divide by the smallest number of moles. In this case, the smallest number of moles is 1.32. So you're going to divide every single one of these by 1.32. Okay. Okay. So once you reach this point, you have to see if you have any whole numbers like these, or if you have numbers that are super close to a whole number, which is like this, something that you can round easily. But in this case, we only have two whole numbers, and the rest are not that close to the next whole number. So when that happens, you're going to have to multiply by a factor to get whole numbers or really close to the next whole number. You always start with 2 and then go up from there. When I tried 2, I did not get the numbers that I wanted, the whole numbers or numbers close to that. So I'm not going to try it, but if you want to double check, go ahead and do it on your own. After trying with a factor of 2, I then tried a factor of 3. I'm going to do it in a different color. Okay. Okay, and you see this number 6.99 can easily be rounded to a 7. So that's actually my final step here, round. And this can actually be rounded to 5. And these stay like that. Meaning that our empirical formula is actually C7, 8, 5, and 3, 0, 6. The second part is saying that an experiment has determined that the explosive has a molar mass of 697.8 grams per mole, and it's asking us for the molecular formula. So I have a few steps here that you could follow. The first one is divide the molar mass of the compound, so 697.8 grams per mole, divided by the empirical formula weight, or the molar mass of the empirical formula that we found here. So I already calculated it based on the numbers that we have here, and it came out to 227.13 grams per mole. Okay, so go ahead and do the math for this. It should give you around 3.07. The units cancel. Okay, so we round this number to 3. And this is a number that we're going to use as a factor to find out the molecular formula. So what we're going to do is that we're going to multiply 3 times every single subscript that we have here for the empirical formula. So 3 times 7, 3 times 5, 3 times 3, and 3 times 6. So this is the molecular formula.